Hello everybody, welcome to the World of Control channel. I'm Mohammed, and in this video I want to model a different system, an inverted pendulum on a card. Make sure that you subscribe this channel because I will make a lot of videos about modeling different systems and designing different controllers for simple systems and complicated systems also. So let's get started. As you know, the inverted pendulum is a system that has 2 degrees of freedom. As you can see in this picture, we have a model, a system that has a cart with the mass of capital M and a pendulum with the length of L and the mass of letter M here. And we have a spring here that is attached to the cart and that has the coefficient of K, and the ground with the cart has the friction coefficient of B. We can describe all the states and all of the actually different positions of the system with 2 degrees of freedom of x and theta. That x is the position of the cart and theta is the angle of the pendulum. For deriving the equations of the motion with Lagrange method, we need to write the kinetic energy and the potential energy of this system. As you can see, with these equations here, we can obtain the kinetic energy and the potential energy of this system. And also, with having the kinetic energy and the potential energy of the system, we can have the Lagrangian of the system, and by applying the Lagrange equation actually to this Lagrangian here, we can obtain these two equations here. But we need to solve these two equations for x double dot and theta double dot to have our state space dynamic systems. And if we solve these two equations, we will obtain these two equations here as our dynamic equations. So with these parameters, with these values here, we are going to simulate our model actually. Okay, let's get started with Simulink. I will import a MATLAB function to import my dynamics. Okay, I have x double dot and theta double dot as an input, actually, and we have m, k, b, l, and g as our constant parameters of our model. And we have x and x dot and theta dot as an input. Okay, now we have to write our dynamic equations in these two lines here. Okay, let me bring the equations. So x double dot is equal to these two terms, m plus m minus m multiplied by cosine of theta. That cosine of theta has to have a square on it, f minus b times x dot minus k times x plus m times g times sine of theta times cosine of theta minus m times L times theta dot times sine of theta, and we have to write theta in all of these functions, sine and cosine functions here. Okay, for theta double dot we have two terms that are summing to each other, g divided by L times sine of theta, and something that is multiplying to the cosine of theta divided by L times this term that is x double dot here. And now we have our dynamics in our MATLAB function. So we need to connect the signals. Let's connect the signals to have our simulation. I will import some constant for having our constant parameters B, L, G, and K. Okay. Let's import some integrator to integrate from these signals. This signal is x double dot, and this signal is theta double dot, theta double dot. We have another integrator. This is x dot, and this is theta dot. This signal is x, and this signal is theta. To showing the outputs of the system, I use a scope block here. I will do some modification. Let's open it at the start of the simulation and make some changes to the appearance of our scope. Okay, this is for x and this is for theta. I will connect the x and theta signals here, and now we can add the values of this power point here. M is 6 kilogram, the mass of pendulum is 1.5 kilogram. K, for now I will write 0, but we will change it later. Be 0 and L, the length of the pendulum 0.6, and the G 9.81. And now we can connect the signals here. X is here, x double dot is here, and theta is here, and theta dot is here. We know that we need some initial conditions to solve the dynamic equations. For now, I will assume that all of the initial conditions are 0 and simulate our model. Let's see what happens. Okay, let's run the simulation. Okay, something is okay. You forgot to import the force. The force is our input that is applying to the cart. For now, I want to assume it as 0. and again run this simulation to see our output. We expect that nothing changes exactly because our system is stable here. For now, I want to change the initial condition of theta to pi third to see what happens. If I run the simulation, now we can see that for 60 seconds, the pendulum is doing like a sine wave here, and x is decreasing actually in negative direction. And now if we set it as 0, the initial condition for the theta, and set, for example, the initial condition for x as 10, um, we know that if the pendulum is in 0 and the cart is in any position with no velocities, we expect that the system stays in those actually values and do not changes. Let's see if this happens here. Okay, we can see that theta is on 0 and x is on 10 and nothing changes. I will change the initial condition here, and I want to import some value for F here, for example 1 Newton here, to applying on the system to see how system changes. We can see the theta and x here. If we add the spring coefficient here, for example 1.5, and run the simulation, we can see that the system is performing like this, x and theta. And if we add some friction coefficients, for example 2 here, we will have our system like these two. We can see that x is stabilizing, for example, around 0.6, but theta is increasing very much. If we increase the friction coefficient, for example, to 50, let's see how the system works. Now we can see that with increasing the value of b, the system is stable now. If we increase, for example, the stop time to 300, we can see that system is stable on some values for x and theta. Thank you very much that you watch this video. Make sure that you subscribe this channel, because I will make a lot of videos about designing different controllers for different systems, and also model some different systems, and simple dynamic systems and complicated dynamic systems. Thank you very much.